Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
And we realized that, one of the key questions we're trying to answer in this work is not which is best, pen or touch, but say instead, if we have both, what is the logic of the division of labor between pen and touch and interface design? And we think that's sort of the right question to be asking about this sort of interface. But I think it goes a little bit farther than that. So that's part of the perspective. I say, Steve Jobs might say, well, if you see a stylus, they blew it. But I would say, well, if you're only thinking about touch, then you're also blowing it. It's a little bit more than just touch interfaces. Just as another perspective on this, this is actually a really old piece of work. This is like 10 years ago now that I did this. We built an old sensing pocket PC with an accelerometer, a proximity sensor, and a contact-sensitive casing. And we had some cool techniques like screen rotation. You could pick it up and it would turn itself on, stuff like that. But sort of in retrospect, if I think about, well, what question was this research answering? It's sort of a similar thing. Like, if you have all these sensors, what is the logic of the division of labor between contact sensing, tilt sensing, proximity sensing in the interface design? Maybe one more example. Let's take Apple's new hit device, the iPad, which is actually a really nice device. When you think about, if you lay it flat on your desk and you touch the icon there, well, what do you think the person's doing? Anyone want to venture a guess of what I'm doing there? Looks like I'm hitting an icon. Yes, correct. But let's take another example. I'll do exactly the same thing. However, now I'm going to hold the device in my hand. So what am I doing there, right? I'm touching an icon, but it's for another purpose, right? And part of the reason this device has such a beefy bezel is because of exactly that issue. So clearly, if you think about what's going on here, which touch is the intentional one, and when is a touch not a touch at all? In one case, you have your finger just happens to be resting on the display. In the other case, I'm intentionally touching it. And the posture of the device is what's telling you the difference between those two. Right? And so if we're only thinking about touch, we can't even answer those type of questions. And this confirms, yes, in fact, your mother was right. Posture is important. So if we really want to design experiences that stand out, we need to sort of get off the multi-touch escalator and think not just about touch, which is important, but also think about how does motion sensing play into this? How does proximity play into this? How does the posture of the device play into this? And all these things together can make really rich new user experiences. So that's great. So now what? So some of you might be familiar with Metro, which is sort of Microsoft's standard visual language for sort of next generation devices. And you can see examples of this if you look up like the Windows Phone 7 demos on the internet. And sort of the principles here is that really the content is the UI, and by direct interaction with the content, that's how you get at things. It also has this notion of laying things out spatially. So as you pan horizontally, you can get at different facets to your information. So it's a really cool piece of work. However, it's really just addressing the visual design side. So the question I would ask is that if this is the visual design for the Microsoft experience, or what we would like to see as sort of next generation user experiences, then what is the corresponding language for input and interaction? And unfortunately, I don't have the answer to that. I wish I did, but maybe this is an agenda for moving forward. However, I do know what I would call it. I'd call it intro. And now the question is, what is intro the answer to? And of course, as we've discussed in this session already, the question is, what is the logic of division of labor between all these different modalities, pen, touch, proximity, motion and postural sensing, as well as different devices, multiple form factors. So that just, touch devices are great, but there's more to it than that. So if we need to move beyond a future where we're just sort of touching things with our stubby little fingers, because that's a nice experience, but there's more to it than that, I think. So from there, I'd like to open up for any quick questions, and we'll keep it brief because we're slightly behind our time, and then pass it over to Andy.
No questions?
There'll be time at the end for more discussion.
Okay. Can I take your...
Absolutely.
Hello, my name's Andy Wilson. So I'm a researcher at MSR, and so I've been involved with the Microsoft Surface project for a very long time. And I think one of the things that's really struck me is is interesting about multi-touch devices and Surface, certainly being one of them, is just the ability to put your hands on the data, and it has a really nice direct manipulation feel, right? And I think it's a very powerful thing. I think we don't really understand why it feels really nice, but one explanation is that it is, in some sense, a simulation of what happens in the real world. And in that sense, it's Surface is a kind of augmented reality system. It feels like you're actually manipulating real objects on the screen. So what I'd like to do today is not talk about that, but I want to introduce a project that we've been working on here recently. This is work with Rvoje Benko, who's sitting down here in front. We call it Lightspace. But what I'm going to do, first of all, is actually very quickly show you some of the heritage of Lightspace. And actually, a number of these videos show systems that were presented and even introduced publicly at past faculty summit events, including this one, where this is actually one of the very first depth camera demos that we did at Microsoft. And so this used a time-of-flight camera. And the thing here is it is a very much has a very direct manipulation feel, because you interact with these cars. The cars are virtual, but the little obstacles that you set up on the tabletop are quite real. The system doesn't know anything about red things or ramps or anything like that. It just knows the range image that we're getting from the depth camera, which is pointed down at the tabletop display. And so some of the fuzziness you see there, some of the softness in that mesh, is due entirely to the noise in the camera at the time. And so you have this very nice sort of constructivist feel to it. You can just basically anything you can set down on the table will be picked up. And so it takes our understanding of what's going on the surface to a new level, really, and it allows us to incorporate real objects. I'll fast forward just a little bit to this. Here's some things that we were doing already with reaching into that volume and manipulating. So here I'm doing this kind of pinch gesture, and I think one of the most fascinating things was this kind of interaction, where you're really interacting with these virtual objects in a very interesting way. And so you can drive the car up. Your buddy can drive the car up into your hand. You can pick it up, and if you're careful about it, you can sort of balance the car in your hand and then drop it. And then from the virtual view, it looks a little bit different. Now, this is you get the sense of again how coarse the sensors were at the time, and the kind of the smoothing you would need. It feels like you took a bed sheet and sort of threw it over your environment, and that's kind of what you're dealing with, the mesh. But I think it's a very nice idea. This is the thing that captured my imagination of this demo, the ability to actually put your hands into this volume and to manipulate these objects. I think that's a really a fun idea, and I'm going to come back to that when we introduce Lightspace. So another very early depth camera demo. Now this is actually using the predecessor to the camera that's in Kinect. Again, it's like a very expensive pinpression toy is the way I like to call it, because what we're doing here is rather than trying to pull out a skeletal model of the hand, we're actually just getting the overall mesh and then moving each of these little spheres into position and then colliding that sphere against the big sphere. So, doing physics on spheres is really easy. And so the nice thing about this kind of thing is that rather than be content with a very coarse model of the hand, we can actually do things that rely on the fact that we know the shape of our hands and we can interact with a ball. We can not even use hands, we can use anything in the world. And so it has a very sort of natural analog feel, and it's that analog component which I think is really nice. Now, going from a different direction, here's Benko. He's showing the work that he did with here in the a spherical version of Surface, and it'll be clear in a little while I'm talking about this. And so basically a surface on a spherical projection system, all the kinds of manipulations you would expect, maybe a few new ones. This is what it looked like. We had a projector and a diffuse projection surface, and then we added a infrared camera and an IR cut filter and so on and so forth to basically allow us to project and see the things on the surface of the ball. And of course, there's some graphical things you have to be concerned about. Here's a globe. Here's a omnidirectional video camera, like for video conferencing, these kinds of things, and then touring through the streets of downtown Seattle. Lots of interesting things there. So we decided next year, we showed the sphere at Faculty Summit 2 years ago, This one we showed last year. What we did is we took the top of the sphere off, and that allows us to essentially project everywhere around the room. And now the problem with that is the projector isn't bright enough, so we decided to throw a dome over it. And so the first dome that we had was this wooden monstrosity, cardboard and binder clips, and just it was a lot of fun putting it together. And now we have these kinds of interactions that are illustrated here, which we showed at Kai this year. That's Benko actually going into it. We switched from the cardboard and 2x4 version to this blow-up one. It's a little bit difficult to see what's going on here, but here's Benko. He's interacting with this Worldwide Telescope. Another thing that was shown often at the faculty summit. And now we have this kind of way to reach into the scene and have this kind of funny notion of direct manipulation here. What we're really doing is taking the standard kind of models that you have for touch and multi-touch input and lifting it into free space. And so everything that we're doing on Surface, we're kind of doing the same thing here. We're generating contacts when you do this pinching gesture. That's illustrated here in the next section. A little more, these kinds of interactions over the surface, and they're picked up using image processing techniques. You can do the same kind of video conferencing interactions. Here's a panoramic image that Mike Sinclair made. And actually a 4-person game that we just recently hacked together. And it's really kind of a fun kind of thing. And you're actually, in some sense, you're interacting with your shadow a little bit. You can actually figure out where you are because you can see your shadow, and that's pretty much the same place where the contact is generated. So that was the dome. Again, we showed that that was last year. Now, Lightspace is the new project that we're really excited about. And the idea here is that we took 3 of the depth cameras that are in Connect and 3 projectors, and we set them up in a 8x10 area, a small room, the size of an office, I guess, and basically clustered them into almost like a chandelier that hangs over the top of the space. We calibrated those cameras and projectors together so that we can basically reason about everything that's going on in the room in actual millimeters, if you will. If you like that, and so we have this world coordinate system, very painstakingly calibrated system here to bring everything into alignment to a world coordinate frame. Allows us to do various kinds of interactions, and these are we're just running through a couple of interactions here, and in the next section we'll explain them. So it's another. Just think about this in terms of direct manipulation. Yeah, so the stuff's actually really in your hand by virtue of the projectors. So here we're emulating surface interactions, and the way we're doing that really is basically just by doing a quick projection of the data, of the mesh data onto a volume that hovers just above the surface. These are just this is just a plain tabletop and a plain piece of foam core on the wall. There's nothing instrumented there. So these are the kinds of interactions we're supporting. That's an interesting one there. What he did is he touched the one object there and then touched the destination, and then that object is basically, the body actually acts as a conduit. Now you can pick up the object, you can manipulate it. That's another way to sort of do this kind of transfer. So the object now has this kind of physicality to it. And the system doesn't know anything about hands, it just knows the shape of the mesh, and so it can do the right kinds of calculations to simulate the rolling of the ball against that piece of paper. He puts it down. You can also hold the ball and then touch the display, and then it's transferred. And the actual particulars of this we'll explain a little bit later. Here's a in-the-air menu. So you hold your hand over a little menu, a little spot on the floor, and as you go up and down, you get a different menu option. And so these are the kinds of things we're looking to explore in the future. The actual using the space, the real 3D space, as an interactive volume, if you will. So maybe, after Microsoft Surface, we'll have Microsoft Volume. So there's some fun things to do. You can shake hands and transfer objects that way, and it's all just looking at the connectivity of the mesh. It's not actually doing any fancy processing. It's using the physical properties of what it observes. Here are the 3 views from the depth camera. The darker it is, the closer it is to the camera, except where it's black, where there's no data. So that gives you a little bit of an idea of some of the noise characteristics of the cameras. And then below we have the actual 3D model. And so he's changing color there once in a while, but for the most part, when you're a single user, the idea is that your entire mesh is the same color, so that when someone else enters the scene, they adopt another color. Here's a small detail of the actual ball moving in the hand. And then the menu, not too exciting there. But this also gives you a nice idea of kind of the noise and and also just the idea that it is actually obeying your motions in a fairly fine way. And this is a detail of what the surface emulation is doing for the tabletop. This projection is just taking a shell above the surface, or above the table rather, and then we're doing the same kinds of multi-touch calculations that we've done with surface. More or less the same pipeline. There it is for the wall. And the way then we detect touching one and then the other is just by looking at the top-down view of this small room, and then we can reason about connectivity from the wall through the space to the tabletop. And that's some details I'd rather not go into, but suffice it to say it's really looking at the physical properties of what it sees, and nothing really more complicated than that. So that's pretty much light space. I think in the near future, what we're looking at is extending some of these interactions that we have with physical objects. Some of you may be familiar with some of the work that we've been doing using physics simulators on Surface. We don't have a lot of that incorporated in this system yet, but we'd like to. The idea of being able to pick up a virtual object and then throw it at the display seems like kind of a fun thing that we might try, for example. So one little detail that we've been looking at a little more closely is, can we use a depth camera to actually detect touch? Now, many of those interactions I showed you had to do with emulating surface input, and we think that that's one thing that we can do kind of nicely. The idea of using the cameras to detect touch generally in your regular environment seems like a really nice idea. And so how good can that actually work? And so that's something we've been studying a little bit. And so what we've shown is that when the camera is about 750 centimeters above the table, you can actually do some pretty good touch if you model the height of the tabletop at each pixel in the sensed image. And so you can actually get down to around a 3 millimeter accuracy, which isn't the world's best touch sensor, but is quite usable. This is image, the depth data, and I'm just going to skip ahead a little bit. Some further processing before you, and then you can actually also raise it a little bit higher. Here's a 1.5 meters, and the nice thing here is you actually are observing a 2 meter diagonal space, so it's actually quite large. So we can contemplate using this kind of setup to do a full conference table setup. And so right now we're looking at instrumenting a standard Microsoft meeting room or conference space with this kind of technology. And then because we're not making too many assumptions about the shape of the surface, we can also do sensing on surfaces that aren't flat. There's nothing going on here in this ball, and we're just picking up, touching this object, which happens to not be flat. So that's really quick. I'm gonna wrap up right now, but I do want to leave you with one kind of question that Banco and I are trying to suss out a little bit lately. Is if everything in your world is interactive, right? We have all this wonderful sensing technology, display technology is coming along. Where does that leave the traditional distinction that they're familiar with between the interactor and the interactee, right? So when you have a touch screen, it's pretty clear that there's the user touches. But now what if the user itself, like as with Dan Morris and Chris Harrison and Desnay's work with Skinput, they illustrated very nicely the idea of having an interface on your arm. Well, so if everything is interactive, including the body, what is the user, right? We've lost this distinction, and so it's kind of a fun thing to talk about and try to figure out where we're going in the future. So I think I'm going to leave it at there. Any questions, comments on what you've seen? A little fast. Thank you.
Wow. Am I up here?
Let's
see. PC. I'm on 6.
6. And you're marked already.
Yep. Andy, that's amazing.
Thank you.
Hey, wait, come over here for a second. That's amazing.
Thank you.
Andy, that's amazing. That's really amazing.
Little close.
That's a little close. This is what this talk is all about. It's about proxemic interaction. I actually gave some preview of this talk to Bill Buxton, who used it in his closing keynote at Tabletop, and he ended up sitting in somebody's lap to bring the point that proxemics is really an important part of the way we socialize with each other, and we have really strong rules for how we regulate the space that we keep between us and how we use that. So I'm going to talk a bit about proxemic interaction. My name is Saul Greenberg, University of Calgary. But even though I'm the guy here, I have to say that these are the guys who've done the work. Nick Marquardt, an incredibly talented PhD student, Till Ballandot, a visiting intern, and Rob Diaz, who works for me. So what I'm going to try to get you to do in the next little bit is to just try to imagine what we could do if we had an ecology of devices with knowledge of proxemics. And by proxemics here, I mean the distance, the orientation, and the identity of nearby people and other devices, and also of other non-digital objects. And the question to ask here is, how can we exploit this knowledge to design natural user interfaces? And this fits really well with what Ken was talking about. This is not, oh, here's another interaction techniques, but this is another aspect that we have to consider about our ecology of what we live. Proxemics is one thing, touch is another, we have gestures, and all these things have to interact together. So just to introduce what proxemics is, in the 1960s, there was an anthropologist, Edward Hall, defined this notion of proxemics. That is, people's cultural perspective of space. And in particular, he was interested in how people manage their interpersonal distance, their proximity from one another. And as a crude way to talk about it, he talked about these zones of space that we have here. So, for example, there is this within 6 inches. That's called your close phase of your intimate space, and it's captured by that photo there. And obviously, when I came close to Andy, he went, "Whoa, this is a little bit too close." And he turned red. And in fact, if you really want to try this, if you're brave enough, turn to your neighbor. Try this. Turn to your neighbor and start leaning toward each other and feel where that discomfort comes. Oh, he kisses people. Yeah, these guys are okay. It's a really strong, visceral reaction that we have when it works. We know when we're with our lovers and we want this, and we know when we're with our strangers and we don't. And this goes to other ranges. So, for example, there's a far phase of intimacy that goes to about 1.5 feet. And this is captured usually by intense conversation. And we know when somebody moves in toward you and they're trying to make a point, we use that as part of our body language. And then it goes beyond that to our personal space. This is usually interactions amongst friends, family members, the talk we have at conferences like this. Going to the social sphere, where it's usually we're interacting amongst acquaintances. And finally into the public sphere, where if we had the space to spread out, we'd actually be quite far apart from each other. So, but you have to realize that it's not just distance, right? Are
these numbers culturally dependent?
Yes, totally. That's what Edward Hall was totally about. It's all cultural. But the other point is that it's not just about distance. Look at where you are. You're in a room. You're actually most of you within a space that would be called almost the intimate personal space. And yet we use other things to mediate that. We use our orientation. We don't sit looking at the person next to us. We use our body language, our eye contact, all of these little rules, how we sit on airplanes, like who gets the armrest, right? All these little rules that tries to give us a bit of separation from the others. So this is what proxemics is about. It's a really rich area. So one of the questions that we had is, how can we use proxemics to mediate interactions? And I kind of stumbled across this in about 1998, 1999, when a visiting researcher, Hideo Key, and I built an always-on video-based media spaces augmented by physical devices. And I'm going to just show you a video of this really early effort. And in the first part, you're going to see how we use physical devices to provide awareness of others' proximity in their distant space. And the second part of how physical sensors can use proximity to mediate privacy concerns over the video channel. So let's take a look at that. I really have to talk to Hideaki about this article. Oh well, I'll get in touch with him when he's back. Oh, he is back. Hideaki, Saul here. Let's meet in the coffee room. I want to talk to you about this article. Okay, see you there right away. Bye. I'll grab my book. Oh, and I see he's left too, so it's time to go.
We can also have a video of the book circuit.
What we're seeing now is what we call the active Hydra unit, based upon some work that Bill Buxton did. And this brings together a video, audio, a microphone unit, along with proximity sensors. So right now, we're together close by each other so we can speak.
Yeah, because we're close together, both audio and video are active.
But if I start moving away, to preserve privacy, audio is turned off automatically. So we can't hear Hideaki anymore. And if I move even further away, it goes into what we call a glimpse mode, where I get only occasional glimpses into his offices. Again, this is a privacy feature that lets me know who's around, but tries to only give a limited view into their space. So we're back together again.
Yeah, right.
So what was interesting about this project is that a real simple input device, rangefinder, you find them in bathrooms now, and taps and other things, was enough to actually make conversation real supple. That, you know, I'm doing my work, and we kind of lean over in their device, we start a little chat, and then we lean back away, and that kind of gives us a sense of personal space, but also that intimate space that we want. Again, that was old work, and more recently, I became excited about the idea of proximity. So in the last year, we decided to tackle proximity as a first-class research project. And because I'm a computer scientist, the first challenge that we took on was to create a platform that would let us rapidly program proxemic interactions. So we built a toolkit called the Proximity Toolkit. Now, based on a high-end motion capturing system, we do things like we capture the location, orientation, identity, and also the touch of objects and people in a scene. And that includes digital and non-digital objects. And from that, we derive higher order relationships, like the relationship between objects and people. We do some ray casting. We actually look at collisions between proxemic zones. We look at movement and all these other aspects. But essentially, unlike what you saw with Andy, the data we're dealing with is actually fairly non-complex. It's about spatial relationships and orientation and identity. So I'm going to just show you a video of what this toolkit gives you, and within that, I'll also show you the first little demo app that we have, which essentially just puts a face on a screen, on a large display, and has it react to other people's proximity. This should start up.
We wanted to explore new interaction possibilities by leveraging proximity and orientation of tools and people in the space surrounding an interaction surface. To accomplish this, we created a toolkit that processes data from a Vicon 3D motion capture system. With the Vicon system, we were able to track objects in 3D space that are tagged with infrared reflective markers. The toolkit offers an intuitive API that doesn't require developers to have any low-level knowledge of the Vicon hardware and only basic knowledge of 3D math. It turns a hardware system that is typically used for recording motion capture into a live input for applications. With this toolkit, developers are able to acquire spatial information about the tracked objects, in this case a hat and a wand, in relation to one or more displays. This information includes position, orientation, distance, collision, velocity, pointing, and touching. We demonstrate many of these attributes with the Vicon Face application. Using position, the eyes follow the moving hat and wand. Using orientation, the face becomes sad when the hat is pointed away and happy when it points back again. Using distance, the mouth exaggerates its existing expression to a point where it becomes angry. Using velocity, the face is surprised by sudden motions of the hat and is fearful of sudden motions with the wand. Using pointing, the wand acts as a flashlight that can interact with the face. Using touch, the face becomes angry when it is poked in the eye. The code is reasonably simple. Your program receives information about tracked subjects through a number of events. Event callbacks provide detailed information about the objects involved. For instance, the callback for a pointing ray moving across a display provides the point of intersection both in 3D space and in screen coordinates, along with distance, angle, and whether the object is actually touching the display. Now let's watch the Vicon Face application in action. Whoa, hello. Oh. Hey, there you are. Ow. Ow, stop it. Not so close. Yay. Oh. Hey. Where'd you go?
So what's really fun about this little application, it's totally trivial, is that when we demo it to people have no knowledge at all about these kinds of technologies, they immediately get it. They understand the relationships and they use their own body movement and other things to experiment with the system. But again, it just shows you what you can do with some fairly low-level information that you can get back to a simple API. So this toolkit let us actually go back to our original goal, which is look at a proximity ecology. And this is the kind of setup we have. We imagined a place where we had a large digital surface. We had people moving about the space who would carry their own portable personal devices. We had informational appliances. We had non-digital physical artifacts that people would carry with them, such as, in this case, we'd call a cell phone non-digital artifact because we weren't actually tapping into its digital capabilities. And we asked ourselves, what can we do with this? So I'm going to show you a series of excerpts from a video we produced that will show how, in this case, mostly a surface will react to the proximity of the people and the objects and also the interrelationships between them in the space. And I'm going to start off by showing how the actual surface reacts to the proximity of a person as it enters a scene from a certain location, moves toward it, touches it, sits down, and so on. So a lot of this work was done by Nick and Till.
In this video, we introduce proxemic interactions. They consider fine-grained information regarding nearby people and devices in order to mediate interaction. We illustrate these concepts through a scenario using our proxemic media player application. The application reacts to a person's presence, distance, and orientation to the display. When a person enters the room, the application starts. As they approach the display, more content of the video collection is continuously revealed. People can explore and select videos through direct touch when standing in close proximity to the display. When taking a seat, the player implicitly switches to full screen view.
So that just gives you a sense of this interaction of proximity. The system is trying to infer what the person is doing and does appropriate things in terms of what it shows, as well as the interaction modalities it presents versus touch, lots of detail for close by, and as you move further back, it shows more of a viewing situation. Okay, let me get to the next screen here. So the next clip, if I can get my computer to go to it, okay, is to show how the surface reacts to the proximity of people to their actual objects. In this case, we'll see him pull out a cell phone and it's actually bringing it in proximity to his head. We'll also see the person change their orientation in terms of a book, and we'll see how the screen reacts to that.
Proxemic interactions also consider a person's relationship to nearby objects. The video playback is paused during implicit actions, such as when the person answers a phone call or when turning away to read a magazine.
And the next sequence is now how the surface reacts to orientation of objects toward it. In this case, we're taking the exact same cell phone, but now we're oriented and bringing it slightly toward the surface.
A person pointing an object to the screen, like a phone, triggers explicit interactions, such as selecting videos from a distance.
So it's interesting that this isn't a special purpose device, it's just an object and it's reacting to those spatial relationships. And we also have the surface reacting to the proximity of multiple people. In this case, as a second person approaches the surface, the information is portrayed in a different form than it was before because it knows both are in the scene. It also takes action when one person blocks the view of the other.
Next, we illustrate proxemic interactions of multiple people. When a second person enters the room, a video title appears to provide awareness about the ongoing playback. When approaching the screen, further information about the current video becomes visible. This information is placed on the screen in a way that allows the person sitting to continue watching the video. When occluding the sitting person's view, the person in front of the display gets control over the video selection. The two views merge when both sit down to watch the video. The video is paused during conversations when both people face away from the screen. Again, a non-digital object is used to select videos from a distance. This time the person uses a pen.
And the final scene is about how the surface can react to the proximity of digital devices. So these are now devices that have content on them, and the question is, how can we actually trigger first awareness that these two devices can talk to each other, that they can actually connect, and then information exchange between them.
Proxemic interactions also consider the distance and orientation of other digital devices around the surface in order to facilitate device-to-device interaction. We illustrate this using a media sharing functionality between a portable digital media device and the large surface. The system provides awareness information regarding sharing possibilities while the device is at a distance. An icon representing the portable device on the large screen changes its position and size depending on the orientation and distance of the portable device to the screen. Full access and information exchange is possible once the person brings the device close to the screen.
So that gives you a sense for some of the work that we've been doing. I just want to say that there is, in fact, a fairly good literature on proxemics, starting from the social theory, and also there's quite a few efforts, mostly individual efforts, and a little bit separate, that looks at the relationship of people and objects to surfaces, devices, and other things. And if anybody's interested in that collection, please ask me, because it's a good starting point for looking at this area. There are a variety of challenges in this. Just to mention a few, we use a high-fidelity sensing environment. The question is, how can we do similar things if we had low-fidelity or limited sensing? An even bigger question is, what are the rules of behavior? A lot of this assumes that the computer is doing an implicit action based upon how it's sensing proximity. And sometimes those rules will not be right. So we have to spend a lot of time thinking about, can we get good rules of behavior, and can we actually alter what happens as part of the interaction sequence? And that's something that Wendy Ju from Stanford was looking at. And there's, of course, the whole HCI of proxemics. How do we actually really do this? And we just started scratching the surface. So that's what I want to leave you with, this idea of thinking about this proximity ecology. We shouldn't be thinking about devices. We've got to be thinking about, we have people, we have devices, we have objects, we have knowledge about the space, and how can we bring this all together in a way that we can actually make sense of it and provide further opportunities for novel interaction. So thanks. While you're setting up, if there's time for questions, I'd be happy to. Do you want to come in? And oh, sorry. Let me give you this.
Thank you. Afternoon, folks. It's really nice to follow such a stellar crowd that have set me up so very well. So I want to start off by thanking our sponsor, Lee Dirks and External Research, and thanking some of the people who've really provided us with a lot of inspiration over the years by manual operation, the combination of pen and touch, and Ken just hit it out of the ballpark as far as I'm concerned in terms of the message that it's not an either-or choice. You ought to have the best of both worlds. The work that I'm going to be reporting on today was carried out by these folks, my PhD student Andrew Bragdon, who's sitting there, Donnie Kendall, who was my undergraduate and now my master's student, and Bob Zelznick, who's a full-time researcher in our group. So I'm going to be talking about two projects, one of which is a continuation of the work that we started 6-7 years ago with Joe Laviola, who's sitting in the audience, then my PhD student and now a faculty member at UCF, on tablet computing, and Joe built us the first really robust and full-featured mathematics interaction program, which did a lot of novel things that we've been carrying on with and that he's been carrying on independently at UCF. And I'm going to show you a sort of a port, but also an extension of that mathematics work to the Surface. The second project is one in the e-humanities, if you like, and it's work that we did in conjunction with Massimo Riva, who is an Italian studies expert, and with our head of libraries, Harriet Hamasi, who's attending Faculty Summit. And it concerns a manipulation of the so-called Garibaldi Panorama, and I'll tell you more about that in a moment. Two completely unrelated projects, but what they have in common is that they both make use of the Surface, and they both try to work with this metaphor of pen and touch as appropriate and sometimes simultaneously. So what's hands-on math? It starts with the premise that computer algebra systems are very nice, but they're not in very widespread use. Most people still use pencil and paper or whiteboards. So why can't we combine the best of both worlds, where we get the kind of informality and sketching ability that we get with a nice piece of paper or a whiteboard, but we get the power of the computer behind it, and that's sort of where we're aiming. What we also need that you get so well with paper is a record of what you've been doing, of your explorations, if you like. So we want the system to remember that for us. We want free-form input. We won't want to be restricted to a little box in which you gesture and then it gets interpreted and it gets shown somewhere else. We want the piece of paper metaphor, the pad metaphor that Ken Perlin popularized so many years ago. So that's what hands-on math is supposed to be, the best of two worlds. And there's an implicit hypothesis here, which is that sort of in the sense of Piaget and many other people who've written about this, when you use your body to manipulate things physically, you aid cognition, and the two processes work together. So if you make mathematics tangible and you manipulate it with your finger, the hope, with your fingers, plural, the hope is that you understand better what it is you're doing as you're experimenting and learning. We also, by keeping a record of what you've been doing and your derivations, we want you to be able to reason about how you got where you got. And this, again, can set us up for this. We want pen and touch to allow us to doodle. So we write everywhere. We have extended mathematics notations. Some of you who've seen the MathPad demos will remember the flick of the hand to get a graph created and so on. I'm going to show you all this first with slides so you have some idea of what you're going to be looking at in the video. It all goes by too fast and I don't really have time to explain it in the short amount of time, so it will be kind of impressionistic. We drag terms of the equation. But dragging is an overloaded operation, and it can have multiple meanings. It can mean factor, it can mean instantiate with a value, and we also use pinch and zoom, pinch zoom to indicate simplification. So there are a number of manipulations that you do with your fingers after you have written the math that indicate to the system what it is you want to do. Dragging is moded in a variety of ways, as I'll show you very quickly in both the slides and in the video. How to lay things out. Do we have an infinite single piece of paper? We've done that, but we also think there's utility in the page metaphor as long as you're not restricted to 8.5 by 11 pages. So we are page-centric. They're virtual pages, and they're a means of organizing and scoping a particular derivation, and different people can have different pieces of paper. One of the neat little parlor tricks that we use is when the paper kind of gets crowded and you want to hide a piece of the derivation, you just crumple up the piece of paper with your thumb and forefingers, and you'll see that. We also have web pages, and as everybody else does, we have a panable desktop, and with a bezel gesture you can sweep up from the bottom, get a panning bar, and then move a thumbnail on that panning bar to locate yourself. So page management includes, of course, being able to delete things, and we use multiple fingers to indicate different things. We use which bezel you are sliding over to indicate whether you're creating a piece of paper, whether you're wanting the panning bar, whether you want to trash a piece of paper, and so on. And those are gestures that you have to learn. I'll talk about the problem of learning gestures in a little bit. This is a vocabulary of manipulations. Clearly, I don't have time to go through them all, and it's a learning curve, as is the case with any gesture-based system. One of the things that Ken and others have experimented with for a long time is the problem of how you disambiguate digital ink from gestures. And we've tried, all of us, a variety of solutions. One of the ones that we had is punctuation at the end of a gesture. We've taken a different approach here because we're featuring bimanual operation where you have both pen and fingers to work with. So this idea of touch-activated pen gestures says you start a gesture and then you get a widget or something that you can manipulate with your non-dominant hand that lets you confirm that it is a gesture versus digital ink, plus pull in additional information. We use a feed-forward system whereby you get to see what the gesture that the system thinks you might be performing looks like. If you don't activate the widget, then it is just digital ink. If you do, then it confirms with what the system thought you were doing, and it gives you these additional choices. So here we show a spacing gesture. You draw like this, the widget appears, and you use the non-dominant hand to say, yes, I meant spacing, and however much you drag, that is how much space you want to create between the top and the bottom expressions. And we believe through user testing that this is a richer way of interacting and also less error prone than our previous punctuation system. Plus, it lets you, since you can be indicating multiple gestures with the same stem, lets you disambiguate between which kind of gesture you want and what kind of additional information you might want to specify with the non-dominant hand. Here you see the rectangle gesture, the system anticipates it, and with your non-dominant hand you slide down to indicate the size of the cropping rectangle. Another idea that we've experimented with is the palm print idea, where you rest the palm on the table, you use your fingers, and either one at a time or multiple fingers at a time, you make selections from a predetermined set of operands or modes, and you can also customize it with your own, and it's probably best shown. One of the obvious ways of using it is to indicate color if you're in a drawing program. Another little technique that we've experimented with is a form of a pop-up radial menu that is initiated when you start a gesture. It does not obscure because it starts out initially transparently, and then if you tap on it in the middle, then it becomes opaque, and you can slide in a particular direction to activate something. And that's probably best seen by looking at the video. And another technique that you'll be seeing, again, disambiguating particular flavor of drag that you're doing, is holding your finger at this angle versus having a greater contact at this angle. And there are two different ways of interpreting What you mean, say you have a window with a graph in it. If you hold it one way and you drag, then you slide the contents of the window, the graph. And if you press down more, then it's a heavier weight kind of thing, as if you were trying to manipulate multiple pieces of paper lying on top of each other, and you'll pan the entire window and its contents. So 2 different meanings, 1 finger, and that's very efficient. Well, we like it, but it turns out that Mac users have learned to work multiple fingers, and so they actually prefer that. Fine. No one technique is right for any particular purpose. Okay, let me run the video now so that you get a better idea of what it looks like.
Provides a pen and multi-touch interface for creating virtual pages that supports the seamless integration of a computer algebra system with digital ink. Gestural input is used to manage pages. A new page can be created by swiping with 2 fingers through the bezel. Here, input strokes are interpreted as geometric shapes or mathematical expressions. An extended mathematical notation facilitates in situ computation over handwritten expressions. An arrow drawn to the right with a pen performs a computation. Touch input is used to reorient pages. Dragging across the bezel reveals a trash can. Crossing the trash can deletes the page. The combination of pen and multi-touch provides for implicit and fluid mode switching. Here the pen is used to write math and then invoke a graph by drawing a gesture to the right with a pen. Touching with the pad of the finger drags the entire graph window. Touching with the tip of the finger pans the contents of the graph. By first pausing, a widget appears for disclosing the angle at which the interaction will switch from one mode to the other. 2-finger pinching can be used to zoom in on the graph contents, for example, to see the hole in the graph at x equals -1. Pages can be resized manually to create more space, or automatically when ink is drawn near the border. Scribble delete gestures are recognized when writing. To explore the x equals -1 singularity, the value of x can be symbolically substituted using drag and drop. The typeset recognized math can be activated by tapping. Then, the resulting math can be simplified step by step, in this case revealing that 0 over 0 is undefined. Pages can be slid off-screen onto an extended virtual desktop, or by swiping across the bezel with 1 finger, the user can pan the entire desktop to make more room without having to close any existing pages. In this polynomial division example, several mathematical transformations are needed. The limited affordances of dragging, squeezing, and stretching cannot express these operations uniquely. For example, the default drag operation for a symbol is to factor it. However, an under-the-rock menu grows semi-transparently from the starting location when an item is dragged. Touching in the middle of the menu activates it and makes it opaque. Choosing the Sigma menu icon switches the interaction to term splitting. Bimanual interactions allow fractions to be split apart. Dragging a term factors it out of all the terms it passes over. Although pages grow automatically, it may feel more comfortable to anticipate space needs and resize manually. Squeezing an expression performs a symbolic simplification. A record of all transformations is maintained using color coding and arrows to highlight what happened at each step. Scaling expressions linearly allows more expressions to fit on a single page. Another way to make space on a page is to collapse a region by folding it. The resulting crease in the page can be tapped on to unfold and restore the page's contents. In addition to recognizing math, other drawing modes are available. A virtual chording keyboard or palm print is activated by placing a hand anywhere on the surface. Tapping the first 3 fingers selects between red, green, and blue drawing pens, although a customized menu allows other functions to be interactively dragged and dropped onto each finger. Hybrid pen and touch gestures can be used to select ink or insert space. When a possible pen gesture is recognized, transparent widgets are shown. By touching these widgets, drawing switches to a bimanual interaction, such as selection or space insertion. Web searches can also be performed. Writing escape velocity is initially recognized as math. Tapping on it converts it to a text breadcrumb. Tapping this breadcrumb performs a web search. Here the user makes use of the space insertion.
In the interest of time, I'll cut it. You can get the obvious cutting of a piece of the web page and pasting it into your page and so on. So we've done an evaluation. People seem to like what we're doing, but an important problem is that none of these systems that rely on gestures are self-disclosing. So we need to continue working with ideas for how you learn, how you discover, and so on. And Andrew's master's thesis on the gesture bar is a very good starting point. Another question for those of us who are pushing the idea of bimanual operation, there's some class of users who prefer to hold a cell phone or their sandwich in their left hand or their non-dominant hand while they operate simply with a single hand, and you have to make that available. For those of you who are interested, we factored out the support software on top of the Surface SDK. We call it StartPad, and for those of you who are interested, we will make it available to you. So I'll skip through that and go on to the next project. Something completely different, which deals with this panorama, which is a football field worth of paper, essentially, that has been painted on. It dates from the 1860s. And it's too fragile to work with. It sits in a air-conditioned space at Brown University, and the only way we could make it available to anyone is to have it digitized at high resolution, and then we play with it on the surface. So let me just show that to you.
This is the Garibaldi application on the Microsoft Surface. We currently have it connected up to an external 72-inch television set, which is standing in for a future touch wall to be used for collaboration. As you can see, any motions I make on the Surface are duplicated on the external display. The main window contains the artwork itself, a panning bar along the top edge, and a hotspot jump list along the right edge. Dragging the thumb along the panning bar allows rapid navigation through the panorama. Indicators at the far right and left show when there's more scroll available. Touching these indicators or dragging against them moves more rapidly along the length of the panorama. Standard multi-touch gestures, such as pinch zooming, are supported everywhere in the application. Here, I'm zooming out on the main panorama to get a larger overview of it. As you can see, the thumb on the panning bar changes size to indicate the area shown by the resized panorama. You may either zoom out to get a larger overview or zoom in to see more details. In both cases, the thumb changes to indicate the appropriate area. The panorama has hotspots along the length of it. Tapping one of these hotspots brings up a list of associated documents. Tapping on a document displays it. At this point, you may interact with it as you see fit, zooming it, panning it around. If you flick it towards the top of the surface, it is also placed on the external display. At this point, all actions which you do on the surface are mirrored on the display. To remove a document from the surface, simply flick it off the bottom. Other document types supported include audio clips, here being used for scene narration.
Victor Emmanuel looks what he is, a bluff man of his word. And
I'm sorry I have to cut it off, but I don't want to overrun my time. So what else you would have seen in the remaining 3 minutes is clipping, audio and video controllers, web pages, and the ability to clip and link, ink annotation. We don't do any retrieval of that digital ink. It is just digital ink at this point. And I should mention that this will be one of the featured parts of an exhibit on Tools for Digital Scholarship that the British Library is mounting starting in October, and that will run for 9 months. It's going to be a very nice exhibition, and it's nice to be featured there. So one of the things we're going to be doing under Microsoft sponsorship is getting rid of any dependencies on this particular physical piece of art and being able to take any large format digital asset, paintings, scrolls, and so on. So it's been a really fun project, and we've gotten a lot of nice publicity for the Surface and for ourselves out of it. Any questions at this point?
In the evaluation of the previous project, the gesture, how long did it take people to get used to all the gestures? What is the learning curve?
Okay, so the learning curve is certainly not 15 minutes. For Garibaldi, people walk up and without any instruction at all, simply by having seen iPhones or their equivalent, they start using it. Andrew, for math, how long to get people comfortable? 20 minutes, half an hour, and you'll make mistakes because exactly how you mode the dragging operation and which does what to the equations takes a little while of experimentation. But the point I want to reinforce is that experimentation is not just making false moves and learning from them. It really is learning. And there is a kind of visceral learning that we think is going to be very important. Any comments you want to make, Andrew or Joe?
Well, the other thing I would say is that, it was really meant to be an exploration of different techniques. So
It's a test bed for different interaction techniques.
So we wanted to kind of see what each technique
Should we use this moment to thank Andy again? Okay, here's the clicker. Okay, cool. Okay, so thank you so much. My name is Patrick Baudisch. Ken suggests I do a bit of a grab back and show a bunch of things, so that's what I'll do. I'll start with something really old, well, kind of old. So this is where I was 20 months ago. I was actually in this group with Ken and Ed and Ram together here at Microsoft Research. And you saw a picture of this yesterday. So one of the two main topics we're looking at in the context of natural user interfaces is one of them is miniaturization of mobile devices, and the other, we're going to see it in a second, is kind of breaking out of tabletop into kind of a Ubicom kind of perspective. So you saw a picture of this yesterday. We made a couple of devices that are manipulated from the device backside. The benefit of this is that you can interact without actually having to collide with the screen content. I'm going to keep this short here. You can shoot people with it. Obviously, this built on earlier work I did together with Daniel Victor and Cliff Forline, so the device called Lucid Touch, so the idea of a semi-transparent device that allows you to see what happens on the backside. So you have visual control, and because of this, you get tremendous control, and you're able to acquire very, very small things. So the cool thing that came out of this was the idea that the whole thing was size independent. So touchscreens can't become very small because the smaller I make a touchscreen, the larger my fingers become in proportion. And that puts a cap on how small a touchscreen device can be. So when you look into your pocket at the spiffy new touchscreen device you just bought, you will probably realize that it's almost certainly larger than the phone you had before that. So that doesn't seem to be the solution right now. On the other hand, by moving to the device backside, we kind of opened up a couple of new interesting interactions. So for example, our version of a touch watch is not one where you touch the watch on the top, but you're actually reaching around and basically sticking your finger through your arm into the backside of the device. And the studies that we ran, and we presented Kai last year, showed that this can be done down to very small sizes. So I'm using this as a setup to the first project I did outside of Microsoft. And the reason is that the whole thing about nanotouch was about the so-called fat finger problem, which is the term we coined a couple of years earlier. The basic idea is that the human finger, unlike a pen, is kind of soft. So if you're trying to touch something, just the fact that your fingertip has a certain extent and it's soft makes it difficult to know what exactly you're touching. In combination with this, you're actually also occluding the content, and so thus you have these large targets that you find on your Windows mobile device or on your iPhone, which are basically all finger-sized. Since we're giving credit right now, by the way, I stole those from Daniel Richter and Clip 4 lines, just to show that we're all stealing from each other here. Okay, well then something else happened in my life. I got into hooked up with the wrong people, so I got bad company, people in suits. You recognize Terry Winograd there, and the guy left of him, this is one of the founders of a big software company called SAP. If you're employed, you probably get your money through SAP. And this name is Hasso Plattner, and he was kind enough to pledge a lot of money to found an institute at the boundary between Berlin and Potsdam, and that's where I've been since. So this is my new group, Fachgebiet, as we say in German, human-computer interaction, and these are some of my students. And so I want to show some of these projects we're working on right now. And the first one I'm going to show is RidgePad, which actually builds directly on top of what you just saw, NanoTouch. And then I'm going to shift gears, and I'm going to look into a bit more what I mentioned earlier, which is to take concepts from interactive surfaces and moving them into like 3D space and rooms and stuff like that. By the way, in the back there is sitting Christian, and I've got your picture in a second here. So this is work that's 80% him here. Okay. So as I just said, touch is inaccurate because of the fat finger problem. So that basically means we can never acquire something with the fingers that's smaller than a certain size because our fingers are so big that they occlude things. And so the first thing we did was we kind of started questioning this. There's a lot of work that's based on this fat finger problem. So we're wondering, given that touch is like this huge new input modality that many of us in this room, we're dealing with touch on a major basis. So is touch really inaccurate? So I'm trying to keep this short. So here's kind of the summary of interesting observations we made. The dashed, and this is to scale, by the way. So the dashed outline is the size of a target that you need on your iPhone or on your Windows mobile phone to properly acquire a target with 98% accuracy. And so the common assumption is that you can't go smaller than that without losing accuracy. The interesting thing that we found is that these little circles in there, actually, this is how accurate people really are. And I can tell you this is 4.7 millimeters, so it's roughly a factor of 3 down from the 11 millimeters. And the interesting thing is that there is a systematic effect that allows us to reveal this, and we can exploit that in touch devices. And so based on this project, we started building devices that actually are much more accurate than what we had before. So, and as a consequence, obviously, kind of the fat finger problem does exist in reality. Obviously, we have this occlusion thing, but 70% of the effect that we thought was caused by it is not caused by fat fingers, but is actually caused by the fact that there are more parameters in the space of touching that we're not looking at right now. So current touch devices, basically like a passive sensing, look at the contact area. They measure this, they take the centroid or whatever they do, and they determine touch that way. It turns out there are a couple of other parameters that matter as well, but by ignoring them, we introduced this tremendous inaccuracy. And so this project is about removing this. So this is actually one of the, this probably is Christian's hand, I guess. So this is from one of the studies that Christian ran. People acquired a little target from different, repeatedly, many times. But we actually spelled out these extra parameters, which is we noted who the person is, and we noted additional parameters such as the angle of the finger between the finger and the pad. And so here's a bit of the summary of this. So if you take all the data together, you get this big cloud, and that basically is your 11 millimeter target, which we probably all come to terms with when designing for tabletop at Microsoft Surface. But it turns out that if you know a little bit more, if you know what direction the user is coming from, then actually this big cloud of points kind of shrinks. So if we know that the user in this case would be located on the other side of the paper, if the user is from the other side, we know that all touches will fall into this much smaller area. And it turns out if we also know pitch and roll, which is basically pitch being this angle and roll being that angle, then this little cloud collapses further, and we actually get these 4.3 millimeters I just talked about a second ago. And so this is exactly what you see here. These 5 little circles are all contact. These contact clouds were gathered under exact knowledge of the finger angles. There's one more parameter that we need to know, which is, this is the same thing for a different user. So different users do it differently here. And so you need to know who the user is. So we have to distinguish them. Otherwise, we cannot apply our compensations to get this very accurate. So that's kind of the inside part of it. Here is something interesting, which is kind of, well, now we're putting our engineer hat on. And so how do you find this out, how this works? So Traditional touch screens get the outline of this. So both Microsoft Surface as well as FTR-based things as well as capacitive, you get the finger outline. And so the trick, what Christian has been doing is he basically took also the content of the touch area, which is the fingerprint in this case. And as you would guess, I mean, the fingerprint gives you the idea of the user, but it turns out it gives you more than that. So here's a little quiz. This is a fingerprint. Try to remember it very well. Okay. How is the user holding the finger in this case? Okay, little hint. Again, here's the finger. Huh? It's the fingertip. That's right. So the finger is very steep, and you get like, whatever, 80-degree pitch. Okay, quiz again. Harder this time. Huh? It's rolled, right? So it's rolled to the left. And it turns out what you just did, machines can do as well, and you can actually buy these things. They're called fingerprint scanners. And if you're not from America, you probably just use one of these on the way in. Isn't it enjoyable that they can participate in these things? And so you can see you actually learn a lot about a contact area if you have the fingerprint. So here you can, is the user rolling or dragging? It's rolling, right? Because you can see that actually the fingerprint is changing. Now that is dragging. So we get a lot of these extra parameters. And it turns out if we're building devices based on fingerprint, which is obviously orders of magnitude more data, but we're actually getting this tremendous accuracy improvement. The fingerprint thing does not achieve the full improvement. If we're having an optical method that we're using with an OptiTrack, we get further improvements. But it's a major factor. It's something like this. You could make like your Windows mobile device on iPhone kind of less than half the size, and you would be able to interact with this as precisely. So this is kind of part of the agenda that we continue to work on. Here's the picture. The glamour shot of Christian was for a paper, so it's a cool shot. Right. Thank you. So basically, we're continuing down this path of trying to make more touch accurate because we are thinking that this is one of the modalities that will be very, very important in space. So for the rest of the time, I'll switch gears now, moving over to this new area that I did not work so much on the year before. We're still here. And it's about tabletop and tangible. So these are two other of my students, Frederik Rudik and Thorsten Becker. They're master students right now. If you just signed up for SIGGRAPH, you might have seen this picture. And so Lumino is a tangible project. What's happening here is that, as we all know in this room, that you have objects, you have tangible objects on Microsoft Surface. It's easy to track them because you have markers at the bottom. What Luminous can do, what regular markers cannot do, is that we can actually track them in 3D. So you can assemble them in a 3D construction. And the way how this works is that these building blocks, which we have handmade so far, contain a specific structure of glass fibers that give them an interesting see-through effect that allows the table to see through the blocks and see what happens on higher levels. So here you can see a little of this effect. You can see that the marker, think of this as being turned around. You're seeing what the table normally sees. You're seeing the bottom of the blocks, okay? So I picked up the blocks and we're looking at the bottom surface. So you can see that there's a marker on it. And you can see, the table can see there is a lumino that's directly touching the table. And if you want to say that black is 0, then this lumino might have the number 0010. But there's something else, which is another lumino that's actually stacked on top of this whole thing. And this little window, if you will, in the bottom one, here obviously on top then, allows you to see through and actually allows you to see the marker of the one below. So here is white, 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 black, or 1110. So the table could say like, okay, well, there's a 1110 block stacked into a 0010 block, okay? The trick of this project is the physical nature of the see-through effect. I'm showing this again here. And I'll explain this to you in a second. So the benefit of Luminos depends on what your context is. If you're coming from a 3D tangible background, then the message to you is that Luminos are maybe an alternative for you. Instead of using electricity, which is what people have used in the past, electric connections to track 3D objects, you could do this on a tabletop computer, and you could use passive blocks. You don't have to replace batteries. They're low maintenance. And you have photons, which are kind of cleaner than electrons in many ways. Less shorts and stuff like that. If you already are in a tabletop background, you're already aware of these benefits because that's what markers give you naturally. But Luminos might be a chance for you to actually go into a 3D space and make more interesting applications by not being flat anymore. So here's the quick overview of how it works. So I don't have to explain this one here. You've got a camera, illuminant diffuser. Normally, the hand reflects the light, so you get a crisp image if things is directly touching the screen. If you're lifting your hand up, you've got more space for the reflected light to diffuse. And as a result, you're getting this blurry image. So this is what a marker looks like if it's in direct contact with the table. This is what it looks like 5 millimeters above the table, and that's what it looks like at 10 millimeters above the table, which means you can't recognize your marker anymore. So the first trick behind Lumino is that we're using these fused glass fiber bundles to keep the light that's reflected off the marker together. And so it prevents it from spreading, and I'll show that in a second. So here is, again, you can see how it's handmade. This is just a bunch of glass fibers that we stuck into this thing. So you have to get this effect. So when the light, and this already shows the second effect. So if this marker is floating there midair, you cannot see it. But if the other luminous in between, you actually have this, the fibers hold the light together, it comes back down. But there's another effect here, which is the fact that they're not straight, but they're slanted. So as the light is piped through, the markers that are arranged in a vertical fashion actually spread out horizontally by the slanted nature of the block. So the table ends up seeing a horizontal layout that the table can actually read. There are a bunch of challenges involved. One of them is how to squeeze that much data into this little space. We made a tremendous number of different designs, including, magnification ones, and then there was a lot about light loss. And we learned actually how to polish glass fiber. This is if you use sandpaper. And the true answer that we learned from a professional company is you need to polish it using copy machine paper. That's the secret to getting really nicely polished glass fiber. So let me skip that in a little bit here. That's the effect. This is not a lens. This is when you look through a fiber bundle that's tapered, actually. You get this effect. And you can see that there is a black one behind the white one. You get the see-through effect. So we made a tremendous number of these different designs. Here you can use kind of a tangible application to color correct a picture, and you can stack another Lumino on it, and you can actually now have different functions of the different layers. The benefit is you can hold them in one hand and actually use them as a stamp and kind of modify more things like that. Kind of the application we like most is, and we called them Legos in the beginning, as the Surface Lumino construction kit here. And even though it's limited to line of sight, it's enough that it actually sees through this little piece in the middle, or in this case the bridge, that it sees through the two legs. Obviously, limitations, you can't stack anything on in the middle, because then you wouldn't have line of sight anymore. And it works by having just a stack of different markers for different pieces. We always enjoy making stuff. So if you're thinking about doing working in a sweatshop or coming to Berlin for a summer, I personally cut about a quarter mile of these things. That's kind of how it works. I could talk like an hour just about how to make these things. It's kind of, I actually brought one if you're curious. So a lot of fun with glass fibers. We're doing some follow-up work where we're looking at deformable versions of these. Okay, so, and the last thing I wanted to show you is this one, which is something we're working on right now, and I'm very excited actually that we just got together with Microsoft External Research with Microsoft Cambridge to kind of work on this. And this is work we're going to show at WIST. And here we're wondering how to extend the concept of multi-touch interaction to, eventually to entire rooms, but in the first iteration on to floors. So what we did is we used an FTR mechanism. You all understand this. Light is injected from the side. It turns out this mechanism of escaping light and pressure sensitivity becomes really, really interesting when you're applying it to feet. This is actual footage what the floor sees. Users identified by analyzing the pattern of the soles. So you can see that the soles are actually different, right? They're different patterns, and these are fairly unique, it turns out. The first time you're getting onto the table doesn't know who you are, so you can register a new pair of shoes. It's really hard to walk the long way to a menu. So what you're seeing now is actually an important feature. This person is drawing a rectangle and someone else walks through the picture, which is really, really one of the trivial but really important functions. The fact that you need to be able to walk on this thing, and that's made possible by recognizing different foot postures, some of which convey that you're interacting, and some of which are just saying that you're walking. So interaction using feet is remarkably precise if you reduce the foot to a specific hotspot at a certain point, which we're programming into the sole of the shoe. And so earlier there was something about, I think Ken was alluding to this. So here you're defining a personal hotspot because everyone has a different notion of how to have this interaction. So these are a couple of side effects that we can do some simple head tracking with this thing by just analyzing the pressure distribution in feet. So that allows you to, I don't know if this is called the Johnny Lee effect. So you can look around objects and you also control that intentionally. In this case, I guess we always do that. We play video games at some point. There you go. Okay, so we're actually going to bring like a little portable version that we made. We're going to bring this to WIST, so if you happen to be there, you're welcome to try this out. So I didn't quite get the chance to kind of make a wrap-up slide, but I think the kind of the message that we're trying to work on right now is that we're really, really excited about the idea of natural user interfaces, and particularly about touch systems. And we're kind of ready to kind of revamp the whole question of smart rooms, if you will. So we want to look at questions like, what happens if I have a room that actually has an instrumented floor? Maybe a situation where I'm like, growing older, and I would like, my kids to look after me, but without installing cameras in my system. And it turns out we can learn a lot about people who live in a room if we just look at these, comparably non-intrusive things. So at the other hand, we're going to look at like interaction through different devices and so on. And so we think this is an interesting research agenda to take the multi-touch technology and kind of marry it back into UbiComp. That's all I had. Thank you so much. And if you have questions. Yeah.
So the multi-toe, all the users were demonstrated.
But you can already say it, and I can repeat the question if you like.
Okay. With the multi-toe, all the users were demonstrated wearing shoes.
Yes.
And so my question is, have you done any work with barefooted or people wearing socks? And
the question is, yeah, I can just repeat that. The question is, have we done work with bare feet or socks? We have done some work. Eventually, we specialized because time was running out. The answer, if you want to know if we can distinguish people, I don't know yet. I mean, there clearly are distinctions in people's feet. It clearly is easier for wearing shoes. We also felt that, at least in our lab, it was quite common to wear shoes. In parts of it, I have to say. But this is a very interesting question. I think it's very interesting to see. I mean, we're actually starting to explore what happens if you lie down on the floor or if you like kneel on it and stuff like that. And we start to recognize people based on that. Daniel.
So the lab is obviously mostly over 20 and mostly, and from the pictures you were sending us, mostly male. If you had a bunch of 15-year-old girls, they'd all be wearing Uggs.
This was a girl in the video the entire time. Okay. But say, nonetheless. I don't know what that is.
If they were all wearing Nike sandals.
I see. Aha. No, there's a limit to it. I think the distinction of the ability to distinguish users is limited to like a reasonable group. That said, a lot of the inspiration for the code that we wrote is taken from forensics. And these people are indeed trying to distinguish basically every human being based on, this one moment, this unfortunate day you kind of had to kill someone and then walk through the mud afterwards. Okay? I do not know yet how far we can push that. But it's very hard. It turns out that the size of shoes is actually clearly an indication, but then the wear at some point could be useful. So we basically, at per pixel pressure, that's what we get. But we are not even close. The limitation is not on the side of the hardware right now. It's entirely on the side of our algorithms. So I think we hope we can improve that.
You had a number of places where you were talking about the system adapting to the specific users as far as touch points and so forth.
Yes.
Have you run your sort of high-resolution touch long enough to see whether users can learn to touch with the system being consistent, and is there an advantage to one way or the other?
Yeah, so the question is, can users also learn this? So it turns out I think users do learn quite indeed. So unfortunately didn't have that slide in this deck, and I don't have it in the backup slides right now. It turns out different users do it very differently. We didn't do enough people to kind of be able to tell that. My guess right now is, if you're doing this for the first time, you get a tremendous length effect. And the longer you're using your favorite touch device, every time you fail, it's classic conditioning, basically. And we have found people for whom this effect is almost zero at this point. And they said, but the N is too small to make a general claim, but they said that they have been adept users of touchscreen devices. If you feel that users should adapt to technology or technology should adapt to users, is a little bit of a personal choice. I tend to think it would be nice if we sold touch devices and people could, at some point you would have configured this profile once, would upload this, and all devices would just kind of be with you in a way. But I recognize that both directions do happen and are indeed possible.
Question? So I think actually in fairness to the next
Yeah.
session, which starts at 2:30, I see some people coming in the back already. We should probably wrap up. So if you have any further questions, please.
And I would say all the speakers, we're probably going to gather here, so maybe we should have questions for everyone, I guess,
so
right?
let's thank the speakers.